So our next presentation is about design strategy for achieving a transparent probe head. Presenter is Svetlana Sejas. She's a research engineer with SV Probe in Arizona. She received the BS degree in electronics from the University of Puebla in Mexico in 2005 and the PhD degree in electronics from INAOE in 2014. In 2008, she was an intern with Intel, and from 2015 to 19, she worked for Isola Co. in developing experiment and simulation-based methodologies for assessing the performance of high-speed interconnects on packaging technology. Currently, she works for SV Probe in Arizona, working in R&D power integrity-oriented projects. So please, Svetlana, start your presentation.
Okay, the presentation is just to present some strategies to achieve a electrical transparent probe head. It will be divided in a brief introduction. Then we're going to review some of the challenges in the design of probe cards. We're going to focus in the high frequency probe card. I will present some examples and some comments and future work. We see in previous presentation how the trend in the silicon industry is for smaller circuits, faster circuits, and denser wafers. This complicates the measurements and assessment of these circuits. And we always can measure after packaging. However, this will increase the cost and the lead time. And when sometimes we don't take account some of the parasitics, that increase the uncertainty of the results. That is the reason why probe cards is really a popular way to assess circuits. Probe cards usually are electromechanical devices that is an interface between the wafer and the tester, which can reduce the price of the measurement and reduce the time because the parallel testing. This has challenges from two different perspectives, the mechanical side and the electrical side. From the mechanical perspective, we need to achieve aspects of contact force, planarity, alignment, lifetime, pitch. And from the electrical perspective, there's thermal dissipation, current capability, and frequency bandwidth. The presentation will be focused in how we can achieve the widest bandwidth, frequency bandwidth as possible. Okay, in frequency, probably I'm talking too fast. In frequency, the main thing that we are concerned is the signal path. We want to control and have a clean signal path. That is the reason MEMS are usually the most suitable option to this type of devices. We have a control path, we know what is the direction and how it is going to change. We have the flexibility in the stack up of the probe head to the option of materials and design techniques. We have a short and long probe, so we can select which is the most useful in the design. And there are available for small pitch from 300 microns to 60 microns, and each of these probes are compatible between each other. And that is why we can mix diameter probes. In addition, we have a reliable and stable contact. All these are good characteristics to start the design for a high frequency probe head. When we start the design of RF probe head, we usually start with the wafer specs. We have a pitch that are the X and Y coordinates fixed by the wafer. We have the bandwidth target that is requested, and we have already the transmission type. We can have differential transmission type of signal and the transmission type. And the goal is always keep as low as possible the reflection loss. That means as close as possible, minus 20 dB, and a transmission a transmission below 1 dB at the highest frequency possible. That gives us to optimize these variables. But how we can optimize it? Well, the reflection loss is the impedance, and we can optimize the impedance to the correct selection of the probes and the right design of the stack up of the probe head. And that will immediately improve the transmission loss. And now the transmission loss only depends on the loss of the prof that can be modified through the length of the prof. Okay. And in the first presentation, we heard about impedance, and the impedance is the main parameter in high frequency. The impedance can describe and predict the performance of any signal in any interconnect. Could be a transmission line, could be a prof, could be a pin, but this describes how the electric field and magnetic field interact. And to visualize it, this is the simple version of the impedance formula. The inductance ratio divided by the capacitance. This is this is only to visualize it because we are thinking in a lossless transmission line or a lossless interconnection. We are ignoring the resistance, the conductance, and the frequency dependent in this moment, but it's just to have an idea. These parameters are linked with the prof head. So the capacitance is defined by the electric materials, and that is the stack up of the prof head. And the inductance is linked to conductors, that is the prof. Also the pitch and ground configuration will modify these parameters, but we don't have control of this. This already set. Okay, so we have two variables which we can modify to achieve the impedance target that we are looking for. We can focus in the dielectric part that is going to modify the capacitance. The main parameter in the capacitance is the dielectric constant. And in the prof head, we have the stack up of the prof head. Usually are ceramic materials that has a really low loss and really stable in frequency. So we're going to focus on the decay that has a good performance frequency too. So we can imagine that we have a case when we have a high impedance baseline. So we need to pull down that impedance to achieve the impedance target. So for that, we can increase the capacitance in the stack-up. So we can modify the layers of the stack-up in a way that the signal see a higher capacitance medium, so that will increase the capacitance and we pull down the impedance. However, we can do it in a different way. Imagine that we have, again, a high impedance baseline that we need to achieve, that we need to pull down to achieve the impedance target. But we cannot modify the stack-up. So the way to do it to the conductor devices is through the probes. In this case, if we have a higher baseline that we need to pull down, we can change the diameter of the probe. That will reduce the inductance of the probe arrive, and we can achieve the target loss, or maybe we are lower that or impedance target, so we can change to a narrow and smaller diameter probe that we can pull up the impedance. So with this basic concept, we can start optimizing or designing the probe head to improve the bandwidth and obtain the impedance that we are looking for. Okay, and this is the first example. We have a probe head which a ground with a signal configuration signal ground is a single-ended transmission, but we cannot modify the probe diameters in this case because there is no more space. We need to keep in mind that we have to maintain this mechanical specs. So we're going to modify the stack-up. Because right now we can see that the transmission is good. We achieve our goal up to 8 gigahertz, but we want the widest bandwidth as possible. The transmission loss is not bad, but if we improve the reflection loss, we're going to see an improvement in the transmission loss too. Okay, so when we optimize the stack-up, what we are doing is modifying the electric constant that the signals in. That way we can modify the capacitance and we can move it up and down through design of thickness and space of the electric layers that are the ceramic eye plates that provide the mechanical support for the probe inside the probe head. All this can be done through simulations and through measurements to validate the results. And we can see how after optimization, we have 3 times wider bandwidth than we had before. Now we are almost 27 gigahertz, 26.5 gigahertz, and we gain like 0.02 dBs in transmission loss. Now we're going to see a different type of optimization. In the probe head, it's usually not all the times we have the same pitch. So we're going to the smallest pitch, in a smallest pitch case, like in this case, and it's always easier to select, to maintain the design constant. So we select the same diameter for all the pitch, for all the probes, like in this case. However, for high frequency, we need to be more flexible because we want a reflection loss close to -20 dBs. That is not possible with this configuration. We are at 5 gigahertz, we are already in -15 dBs. And in transmission loss, we are close to 0.6 dBs at 7.5 gigahertz. That is the baseline, so we need to optimize. And now we're going to focus on the optimization to the inductance. That's mean the probes. In this case, what we did is change the diameter of the probe for a larger probe. We had a higher impedance before, so with this change, we can see how we can achieve -20 dBs all up to 7.5 gigahertz, and we gain 0.2 dBs in the transmission loss. It sounds like a small amount of energy, but in high frequency, it's really appreciated when we can gain a little bit of energy in the transmission, because we can reduce any amplification in other parts of the system. Here is an example of the real world. I hope it's the left for all. We have the measurement of a profit. This profit is not optimized for high frequency. It was a profit that we used to test it. So we have a ground configuration with a 250 micron pitch. So we measured this after calibrate the VNA and all the steps that is done. And we measured like it was a really short transmission line. And the measurement are showing in black. We can see how the impedance is really not matching high frequency. We have high reflection and a high transmission loss up to 10 gigahertz. The first step to optimize this design is, okay, we have the measurement and we need to correlate with simulation. We know the probe, we know the stack up, and we start the simulation to have a reference to optimize. After doing that, now we have the results in red. We can see how the simulation reproduced the measurements accurately up to 10 gigahertz. With that baseline, now we can start the optimization. We see that the diameter, it wasn't the best option for this case if we want to work with this profit at high frequency. In this case, we did not modify the stack up because the profit was already built. So what we did is optimize the probe side. We went to a larger probe for the ground and a larger probe for the signal. In that way, we reduced inductance by a wider probe of the signals, and we increased the capacitance, reducing the space between ground and signal to achieve the impedance that we were looking for. And we can see how the reflection loss was improved was improved all the bandwidth, but now we have -20 dBs up to 8 gigahertz, 8.5 gigahertz, and we can see how the transmission loss just improved to achieve -1 dB at 10 gigahertz. Okay, these are just some comments that we need to think that the profit is only one part of the complete interconnection of a complete system. So as transparent, we can design this probe head or this part of the system, we can have more tolerance for, or a larger tolerance for the PCB and the space transformer. And we know that each part of the system has their own challenges. That is why we always have to think about how to improve the impedance, because that maintains the signal integrity in the system. But we always can tune this to the right selection of geometries and the correct selection of the materials to achieve the impedance. In the future, we're going to test this concept with the space transformer with a more complicated configuration of grounds, because we now test ground signal ground. And we're going to add space transformer so we have a more complete interconnection channel. I think that's all.
Thank you very much for this nice presentation. One question, you mentioned that impedance really is dependent on material and geometry. Can you say a little bit about the limitations of these two parameters, as well as what it means on cost if you start doing fancy geometries or fancy materials? Can you maybe help us to understand this?
Yeah, of course. Okay, there is some limitation in the selection and optimization of the profiles. For example, we can see here that we cannot have any diameter probe to reduce the inductance, because we need to maintain the stability of the guide plates. And that means that it is able to drill in these guide plates, and it is able to have a wall thick enough to maintain the probe inside of the hole. The other thing that we need to think about is we want a zero length probe, but that is not possible either, because first we have to think about that the wafer and the probe need a distance to be safe, and we cannot break the wafer. That is one limitation. The other limitation is sometimes there are components below, really close to the probe head and below the PCB, and between the PCB and the probe head. So we need to increase a little bit the length to avoid these components. That is another limitation. The other limitation in materials is like, we like to work with ceramics because there are really low loss materials and really stable in frequency. And we have a selection of, there are really a wide band of decays in this type of materials that go from 5.5 to 13. That gives us a lot of play to obtain and modify the capacitance as is needed.
Okay, thank you. Then second question. Obviously, once you drill these holes, there's always some accuracy related to the mechanical process. Have you done some study about how these mechanical tolerances are impacting your impedance and your electrical performance?
Yeah, we try to keep really center in the path, and the probe will be landed in a range, I think it's 8 microns. So that will modify a little bit the pitch between, or the space between the ground and the signal, or between the grounds, but that only impacts maximum 2 ohms. We have been simulating and testing because it's a parameter that is really important for us. So it's maximum change of 2 ohms.
Okay. Then I think we have no more questions. Thank you very much.
Thank you.
One last is coming up.
Okay.
Are you using a regular ground signal ground probe to measure the pins?
Oh, in this case, for them, we can select any type of tip of the probe in our case. That is the flexibility that we have. We can change geometers and we can mix it, and we can change the electric and we can change tip probe. In this case, we measure a flat tip because it was easy for landing the coplanar probes.
Thank you.
In conclusion, I'd like to very much appreciate our sponsors who've made this event possible and allowed us to do this without registration charge. Our premier sponsor is Kohu. Our emeritus sponsor is Johnstech. Our honored sponsors are ISC, iWin, and TSC. Our distinguished sponsors are Backer Hot Watt, Innovative Circuit Engineering, JMT, Nidec SV TCL, R&D Altanova, and UI Green. Our exhibitors sponsors are ELES, MJC, Phoenix Test Arrays, and Smiths Interconnect. So thank them once again, and when you have an opportunity, please thank them. An extra special thank you to Kohu, our premier sponsor, the market leader in test interface solutions for the most challenging applications. Our honored sponsor, ISC, global #1 total test solution provider. And iWind, the test probes provider for high signal integrity at extremely high speed test. And once again, I would thank all of you for attending and participating in this week. Look forward to seeing you all online the week of October 25th for TestConX China, and then March 3rd through 9, 2022 for our in-person event in Mesa, Arizona. So I wish everybody a good rest of your day. Thank you for your participation.